Hey folks, I'm Domotro. Welcome back to my combo classroom where we are in the final week of grade -1, which is related to why I have a tent in the background and why I've cut the second half of my hair to catch up with the first half of that haircut. And why my lab coat is back there, more destroyed than ever. I actually have a fresh new lab coat ready for the upcoming grade -2, but it doesn't make sense to put that on yet. We're still in the final week of grade -1, so we're sort of between lab coats. Now, in this little video, what I'm going to go through are some more of the answers and problem solving tricks to get to those answers of some questions on the final exam that I made for grade -1. That was presented in a video on the main combo class channel, which if you haven't seen that, first watch that. It's linked in the description here. And if you do want to try that yourself, I highly recommend puzzling your brain through some of these. But for those of you who either did try already or don't think you're going to try, I'd like to not only show the answers to them, but also show how to get to those answers, because some of these reveal some interesting patterns or ways that you might solve a problem. So, in the set of questions that I'm going to answer in this video, which is part 2 out of 3 videos that I'm making of these answers, I'm going through questions 6 through 11, and I picked that stretch because these questions are about counting in different bases. Now, we count our numbers in a base 10 system, where the places in a number basically represent the ones place, then the tens place, then the hundreds place, which really is 10 to the 0th power, 10 to the first power, 10 to the second power. So in another base of these basic types we're talking about here, we'll have each place in the number represent the ones place still, because that's the base number to the 0th power, and then the base numbers place, the base number squareds place, and so on. Now, the first question here asks about the largest prime number known to humanity. And although I don't necessarily expect people to know many details about this prime, it's good to know that not only the largest, but the top few largest primes that we've discovered as humans are all of the same type, a type known as a Mersenne prime. They're one less than a power of 2. They can be written as 2 to the power of something minus 1. What does that mean in binary? Because here we ask, if the largest prime number currently known to humanity was written down in binary, how many of the digits in it would be a 0? And a number that's 1 less than a power of 2 will be 1 less than a number of this form, 1 with a bunch of zeros. That would be a power of 2. And 1 less than that ends up being a string of ones. The numbers that are 1 less than a power of 2, as I've shown before, are these hyper-11s, or generalized rep units in base 2. In binary, numbers composed of just ones could be seen as the sum of a bunch of powers of 2, but they're also 1 less than the next power of 2. And since this prime number is of that form, we know that this prime number will be composed of only the digit 1 and will have 0 zeros in it. So the answer is 0, unless you were to count the infinite amount of leading zeros or the infinite amount of zeros after a decimal point for an integer, which we're not going to count those because when we analyze the digits in a number, we're just looking at the chunk that represents the number without those leading or trailing zeros. But theoretically, if you counted those, the answer would have been infinity zeros. So that would be an alternate form of answer. If you want to cheat, is say, oh, it's an infinite amount. But we'll assume for these questions, we're not counting those leading or trailing infinite zeros, just the digits that we need to represent the number, none of which in this case are zeros for that prime. Now our next question says, if we wrote each of these numbers, described here in our normal base 10 terms, in base 12, how many zeros would each end in? And we have first 6 to the 10th power and then some others. What does it mean to end in a 0 in base 12? It means for each 0 you end in, you're divisible by a power of 12. So if I have 1 0 at the end, I must be a multiple of 12. If I have 2 zeros at the end in base 12, I must be a multiple of 12 squared. And if we follow that logic, we can see that for this third question asking, or the third part of it, a number which is divisible by 12 cubed, but not divisible by 12 to the 4th power, well, although there's many numbers that could fit that definition, all of them will end in exactly 3 zeros in this base, because 3 zeros at the end of a number in base 12 means we're divisible by 12 cubed. But if it had been divisible by 12 to the 4th power, then we would have had a 4th 0 there or more within the number. And so knowing that it's divisible by 12 cubed but not to the 4th power tells us there's exactly 3 at the end. Now for these first two parts, it's going to help us to tally up how many 2s and 3s am I getting with each of these numbers if I break them down to their prime factorizations, because 12 is made up of 2 times 2 times 3. So for each 12 I need to be divisible by, in this multiplicative structure, I need a pair of 2s and a 3 in my prime factorization. Now, 6 to the 10th power can be written as 2 to the 10th power times 3 to the 10th power, because that is its prime factorization. Now, if we look at this, we have 10 total 2's multiplied together, and we need a pair of 2's for each 12, paired up with a 3, but we have more than enough 3's to cover those pairs of 2's. There are 5 pairs of 2's out of 10 total ones, meaning that we are going to have 5 4's essentially by those pairs of 2's, each of which has a 3 to pair up with and get us a 12 it's divisible by, meaning this will have 5 powers of 12 it's divisible by, or 5 zeros at the end. 15 factorial. We can tally up, multiplying all the numbers from 1 through 15, which of these will contribute 2's and 3's. Like 1 times 2 gives me a 2, times 3 gives me a 3, times 4 puts 2 more 2's in the mix, prime-wise. Now times 5 doesn't change it, times 6 gives me 1 of each, the next one that contributes is times 8 gives me 3 2's, and then 9 gives me 2 3's, 10 gives me a 2, 12 gives me a pair of 2's and a 3, 14 gives me a 2, and 15 gives me a 3. And by tallying these up, I can see I have 6 3's, but not quite 6 pairs of 2's. I have 1, 2, 3, 4, 5, and a little extra. 5 pairs of 2's plus an extra 2, but the extra 2 will not be enough to make a 12. And so we have 5 pairs of 2's, each of which does have a 3 here, so our answer is 5 again. Now here the answer written in how many zeros would be 3. So those are our answers to number 7. What about number 8, where we're asked, write the number -5 without needing a minus sign or negative sign in these following bases: base -10, base -2, and base 2i. Well, in these numbers, let's think about what the places represent. Here in base -10, we have a 1's place, which is that to the 0th power, then a -10's place. So we're going to need to take one of the -10's, but then we're going to need to add back 5 of the 1's place. And by writing what looks like 15, but we'll call it 1, 5, in base -10, we're essentially adding 1 -10 and 5 1's, which gives me -5. In base -2, we need to go a few powers deeper. We can see we have a 1's place, a -2's place, a 4's place, and a -8's place. So we're going to need to take a -8, add back 4, subtract 2, and add 1. And if we string this all together, we get -8 plus 4 plus -2 plus 1, and that does give me -5, meaning that in this base, it's what I could call a hyper-11. In base -2, this hyper-11 is the number -5. An interesting twist on how in base 2, the hyper-11s were the numbers 1 less than a power of 2. So here in base 2i, we have a 1's place, a 2i's place, and then 2i squared for that place. And 2i squared is -4. So we're going to want to take not just one of the -4s, but two of them. And you may have needed to see my video about this imaginary, or, this base 2i, and in general how bases like this would work, or read up on other resources, like there's some good things written by Donald Knuth about stranger bases such as this one. Well, you're going to actually end up needing 4 different symbols. Typically 0 through 3 are used to convey all of the numbers in base 2i. So we are going to allow ourselves the digits 0 through 3 in this type of imaginary base, sort of because 2i can be written as square root of -4. And that square root of -4 ends up making us need to treat it almost like base -4, which would use the digits 0 through 3. Now, we're going to take 2 of the -4s, none of the 2i's, and then 3 of the 1's. And with 203 as a string, we get -8 plus 3, which gives me -5 in that base. Next up, we have in base 6, how many minimal pan-digital numbers are there? And I clarified this because pan-digital is a known thing. It means containing every digit in the given base, but minimal was my personal term to describe the ones with the minimal amount of digits possible for a pan-digital number in that base, which would mean using each of the digits only once each. So essentially, we want to know how many ways can base 6 have numbers composed of 0 through 5, each used exactly once. So normally we might think we could take 6 factorial to find how many ways we can permute or arrange 6 items, because factorials do enumerate the ways of how many permutations a set has or how many orders you can put it in. But we can't quite take 6 factorial because the first spot out of the 6 digits we're going to want can't be a 0 in these normal representations of numbers. If we included that, we'd include all of the infinite leading zeros. So we have to assume with pan-digital numbers, we're not including the infinite amount of leading zeros, and we're just going to need that first place to be one of the digits 1 through 5. So there are 5 options for that first place. The other 5 places can be whatever remaining 5 digits I have that weren't used in the first place, arranged in any order, because now the 0 could be any of those. So the remaining 5 we can say are 5 factorial arrangements left, and we can either phrase this answer as 5 factorial times 5, or as 6 factorial over 6 dividing 6 after 6 factorial. These are the same result. Divided by 6 factorial, we need to multiply it by the 5 as well. So this is going to be a worse phrasing. So let's say that 5 factorial times 5 is a much better phrasing. But there are ways to write it. You can leave comments if you want to write it other ways involving a 6 factorial divided by some stuff. Now, here what we have is the number 600, and I'm going to write it out as 600 so we know I'm talking about that amount of a thing, because if I write 600, some people might think I mean in base 6. I think base 6 would write that 2400, something along those lines, but in our base, we'd write it 600, our 600 different minimal pan-digital numbers in base 6. Now, in base 9, what are the possible last digits that square numbers can have? This was something related to what I've discussed with modular tables, where we've looked at a modular system, a set of remainders numbers can have after division, very similar to the last digit they could have in a given base, and what happens when you multiply those or add them and such. And in fact, in a stream that I did earlier today, which will be visible on this channel as my streams, but sometimes it takes a little while to process with the chat and to process the HD, I went over some modular tables, and we have here a mod 4 multiplication table, where in mod 4 I can be congruent to 0, 1, 2, or 3, and what happens when I multiply each of those by each other. And when we look at square numbers, we only need to imagine the diagonal. What happens when a 0 times is a 0, when a 1 is multiplied by a 1, when a 2 is multiplied by a 2, or a 3 is multiplied by a 3 in that case. And we saw in mod 4, these things that are the diagonal, which are technically known as quadratic residues of a given mod, were only 0 and 1. You can watch the stream for more details, but it's pretty neat patterns that emerge because of that. But here in base 9, we would need to make a much bigger table. Since we're just focused on the diagonal, though, what we can do is make a little list of all the possible values that a number could be congruent to in mod 9, which tells us the patterns about the last digit of base 9. And in this mod, or last digits of bases, we have all the values between 0 and 8 as our possible integer values. Now, if I square each of these in the mod, what happens? 0 squared stays 0, 1 squared stays 1, 2 squared becomes 4, 3 squared would be 9, but in this mod or base, the last digit or the mod congruent value is 0 because we're in mod or base 9. 9 wraps back around. And here 4 squared would be 16, but how much more is it than a multiple of 9, we can think? It is 7 more than a multiple of 9. Now, how about this? 5 squared is 25. That is also 7 more than the latest multiple of 9, which was 18. Now, 6 squared is 36. That is a multiple of 9, so we'll put a 0. 7 squared is 49. The nearest multiple of 9 was 45, making that 4 higher. And 8 squared is 64. The nearest multiple of 9 was 63, making it 1 higher. So these are the possible values that a square number could end up congruent to, and it tells us the patterns of the last digit. It tells us that in base 9, these are the last digits a square number can have. And we didn't ask for the repetition, so we can delete any repeats, and these are all repeats. So we're left with 0, 1, 4, and 7. And those are the possible values that a number could be congruent to in mod 9 if it's a square number. And they're also, because of that, or linked with that, the last digits a square number could have in base 9. Finally, for our base section here, we have in base 10, what is a 9-digit number whose fourth power is a palindromic number? Now, I asked for a 9-digit number, so we're going to need to not be looking at trivial cases like 0 and 1 being palindromic, or tiny things like that whose fourth power stays similar to their size. This is going to be a 9-digit number whose fourth power gets really big, and I'm going to need to know a pattern for what makes a palindromic number. Now, this is one that I revealed in an episode on the main combo class channel that if you didn't see that episode, you might not know this, or if you hadn't read other resources about this. There is one type of number that is discovered that does this, and in fact, as far as I know, there's no other discovered answer to this question yet. But as far as I know, it also hasn't been proven this is the only answer. Well, let's say I didn't know the answer. I might try something very simple. I might try something composed of only ones. Now, if I take the square of this, it's a palindromic staircase. But the fourth power of this is going to not be palindromic. It's going to break at some point. What about 1 followed by only zeros? That's not going to work either. But it turns out if you try 1 followed by only zeros until the end, And then you have another 1, making 7 zeros sandwiched between a 1, the type of number I call a hollow 11, to match my nickname of Hyper 11s for numbers like this. Well, some of these hollow 11s have very interesting traits. Again, like how the Hyper 11s in binary were very important, there will be a future episode about how certain hollow 11s in binary relate to which shapes you can construct with a straight edge and compass, as well as relating to the roots of unity we discussed and other really cool things. Now, with this number, you can try plugging that into a calculator if you want. You're going to get 1, bunch of zeros 4, bunch of zeros 6, and then it's going to be palindromic, back to 4s and 1s with a bunch of zeros between. So this is the, as far as I know, only discovered number whose 4th power will result in a palindromic number. And I think that's pretty fun. And those are all of the purely base-related questions. There are other ones related to mods on this exam that will come up in the 3rd part of this mini-series of videos explaining the answers. I'll put out in 1 or 2 days from now that 3rd part going through the rest of the math questions on this exam. And what I'm mostly spending my time on this week is editing that wild finale episode I've been putting together that not only compiles the adventures I've been having this month with this tent and haircut and lab coat and such and a field trip and more, but also some flashbacks of some rare stories of putting together combo class that I've never shown before. So there's a lot of rare personal footage on that. It'll be coming close to the end of March so that I can get it all edited nice and good. It's going to be close to an hour, if not an hour. And I hope you all watch that like a short film, because it's a big project to me. It's the longest filmed, edited project I'll have ever put out, probably, among many projects I've made. So please watch that and see what it was like for me to make this grade and how the transition is going toward the very interesting looking grade -2 I'm planning. And I will catch you again in some other videos on this channel too, like the answer video and the stream I'll be doing this Thursday at 6 p.m. Pacific time. So thank you all for joining me. Love you all. And I will see you again in the next one.